Now, basic questions that GIS can answer. So where is what? So you can easily do that through a cartographic map. By just checking a cartographic map, you can easily determine the location of a particular area. Now, what relationship exists? So here you can conduct spatial analysis to determine the relationship of different variables. Third is, where is the best? So this concerns suitability analysis. Next is, where has it changed? So this involves temporal analysis, which means that you have to have temporal or time series data. What affects what? So this involves system models and what if scenarios, or you can do this through simulation. So what relationship exists? As we said a while ago, this concerns spatial analysis. So examples are these types of questions. What is the area of crop A plantation located in steep areas? So in this question, you need to have first two types of data sets. So the first is type of crops, and the second is slope data. Now, before intersecting these two data sets, you need to define first steep slope. So for example, if we define it as those greater than 30%, then that's our definition of steep areas. Once you have defined your steep areas, we can now intersect the crop type and slope classes, then extract crop A and slope greater than 30%. Then we can calculate the area. Now, the second question, what are the flood vulnerable barangays in City A? Again, we need two types of data. Flood hazard class, showing you the different levels of vulnerability, low, medium, high, and barangays in City A. Once you have these two types of data sets, you can intersect, then identify the barangays. So just a list. Now for the third question, is the forest cover more intact in LGU A than LGU B? Again, we need two types of data here. One is forest land cover, and the other one is LGU types or classes or municipality data. Then first we need to define intact. Intact could be defined in terms of forest area or forest density. So forest area divided by the municipal area. Then we can intersect the forest cover and LGU data, then calculate the area or the density, then compare which is bigger. Now, where is the best type of questions? So this is more on suitability analysis. So an example is this question, where is the best location for planting crop A? In here, we need to set the criteria which determines suitability. So for example, soil type, climate type, proximity to water sources, and slopes. So from those four data sets or layers, you can identify the most suitable areas by combining or overlaying these four layers together. Now for the second type of question, where is the most suitable area for locating farm to market roads? Again, In here, you are required to set your criteria. For example, proximity to production areas, proximity to markets, proximity to roads, slope classes, and so on. And then you overlay these layers together to come up with the most suitable area. And the third question, where is the best location to put up a livestock farm? Again, you define your criteria, for example, slope, water sources, away from built-up areas, wind direction, and then overlay them, and then come up with the best location to put up a livestock farm. Now we go to types of spatial analysis. So in here we have 4: queries, measurements, transformations, optimization. Now queries are the most basic of analysis operations, in which the GIS is used to answer simple questions posed by the user. So the user interrogates the system to obtain answers. And this is done by sending a formal SQL or standard query language request to a database. Querying also involves attribute querying. So in this example, you have here select by attributes. Now measurements. You can measure certain properties of objects like length, area, or volume automatically using a GIS. However, just a precaution, because of the curved surface of the Earth, a GIS will almost always underestimate the true length of a geographic line. So the length of a line in a 2D GIS representation will always be the length of the line's planar projection, not its true length in 3D. And the difference can be substantial if the line is steep. Now, the area of a parcel of a land is the area of its horizontal projection and not its true surface area. So again, the area is also underestimated. Now, transformations. So these are just converting your original data sets into newer data sets. So you can combine them, you can compare them to obtain new data sets. So another example of a transformation type of spatial analysis is map reprojection. So reprojecting from one projection to another. Also merging and clipping. So edge matching or merging. These are just combining maps captured in smaller portions into a larger map, as shown here on your left image. Then clipping or breaking down a large map into even and smaller map units, as shown here on your right. Then we also have proximity analysis, which are used to highlight or determine areas of influence of certain features or events. And examples of these are buffering and spread functions. So buffering is just setting a buffer distance away from a point or a polygon or a line to determine impact areas. We also have overlay analysis, which is just a technique which identifies sites that meet inclusion criteria or those criteria that a site must have, or exclusionary criteria or those criteria that a site must not have. So for example here, if we want to create a flood hazard map, then the layers are your slope, your soil and rainfall intensity. So we overlay them together to come up with a flood hazard map. Now for the exclusionary criteria, this involves mapping of your environmental constraints and sieving out less important factors. Now for arithmetic overlay, you can do an arithmetic overlay of your flood hazard, your landslide hazard, your storm surge hazard, and tsunami hazard to come up with a multi-hazard map. And the second type is your logical overlay, which involves finding the areas where a specified set of conditions do or do not occur. So for example, here we want to find the suitable agricultural land given certain criteria of soil type, drainage characteristics, and slope, and also determining the ideal site for residential area given the slope and absence of hazards, as shown here on your right image. So these are also some analytical maps which can be derived from overlay analysis. A while ago, we discussed about flood hazard, but you can also do an overlay analysis to come up with an erosion potential map, and the sources of data or the layers that you need to collect are rainfall intensity, vegetation types, slope, soil types, as well as land capability classification or land capability maps, which is dependent on your soil erosion, the potential flood, and soil conditions. An example of an analytical map is your development constraints map. Here we have an example province of Bohol. So this is just a composite map that shows areas not suitable for built or urban development. And the development constraints map is derived from the overlaying of the forest zones, protected areas, steeply sloping areas, flood-prone areas, areas with natural hazards, built-up areas, other sensitive areas, and SAF-DZ areas, or areas of prime agricultural lands. And the fourth type of spatial analysis that you can do in GIS is optimization. In this case, network analysis, which deals mainly with routing problems. For example, shortest path problem, or finding the optimal path or the fastest way from point A to point B. And also some location allocation problems, where to locate and how to allocate demand for service to central facilities, such as P-median problem, which is just locating P number of facilities such as the sum of the distances is minimized. So the objective function is to minimize the sum of the distances. And this is usually performed for the planning of public and private facilities, such as postal offices, city halls, etc. Now another type is what we call a coverage type of problem, which seeks to minimize the farthest distance traveled. And this is done for planning emergency facilities, such as hospitals, fire stations, and so on. Now your network analysis can find the best route. So example here, finding the best route for a bus to pick up students. And the options can include multiple stops and can include barriers such as one-way roads and so on and so forth. So another Example is finding closest facility or finding the closest hospitals to different schools. And options are you can set the number of facilities to find. So for example, closest 3 hospitals to each school. And you can introduce some cutoff distance, closest hospitals within 3 kilometers. Also, you can find service areas, such as finding the coverage area of warehouses or depot. So in here, you build polygons that represent the extent to which different locations are closest. Can be used to find the coverage area of warehouses. So in here, you can also introduce cutoff times within a 20-minute drive time, or you can set breaks, 5, 10, and 15-minute drive times. So the ultimate result will be a map showing you isochrones, or those areas with equal times or driving times. So the different colors here represent same times. So for example, for yellow, it's 5 minutes, red for 10 minutes, and purple 15 minutes drive times. Now these are just other GIS applications. So network travel times and traffic speeds, traffic volumes and flows, incident detection, pavement management, and so forth. We will discuss this in the succeeding slides. But in here we have a figure showing you travel times from the pinned point and showing you the different travel times from the pinpoint to the different areas in hexagons. So the dark colored areas there represents travel times of more than 1 hour. So this is just an example of the DPWH road traffic information, one of the GIS web applications being used by DPWH. And in this figure, you have here the annual average daily traffic in 2017. But of course, you can check or select other data as well. Also, an example is accident hotspot analysis. So in here, this is used for identifying black spots of accidents involving motorcycles and tricycles. And the source of data for this one is, I think, the MMDA database, MARAS. And the accidents were plotted in Google Earth and then processed and then analyzed using kernel density analysis. And we have here the resulting figures for the fatal, injury, accidents, and property damage. And the red areas there represents where these different types of accidents are concentrated. So for example, for fatal accidents, you can easily see that Commonwealth Avenue is one of the most dangerous streets or avenues in Quezon City. So this is another example for a road incident data system. Driver system, data for road incident visualization, evaluation, and reporting system. You can visit their website, but you have to register. And it basically shows you the location of where accidents or road incidents are concentrated. This is an example of monitoring of vector-based disease. In this case, dengue. Okay, so dengue, it's the same concept as the previous slides. So identifying hotspots or cases where dengue are high. It's indicated by the red colors on your right image. So this can also be applied for pandemic or COVID-19 mapping. And also you can use your smartphones for pavement maintenance. As you know, estimating road roughness is a very costly activity. So the idea here is to use smartphones to estimate road roughness. So in here, this is a study by one of my students, and what we did was to use two cell phones or two iPhones installed at the front, the dash, and the rear axle, and we also installed a VIMS system, which is a well-established equipment developed in Japan, which measures road roughness so that we can compare the results later. And this is our results. So case 1, if we use acceleration only, the fit of the data is around 0.618. The actual IRI, so this is the VIMS data, and the calculated IRI is around 0.618. But if we use acceleration plus speed data, so the fit will be much higher. So this shows that the iPhone sensor has viable accelerometer that can be used to measure road roughness, and acceleration and speed parameters results in more accurate IRI values. So this shows the side-by-side plotting of road roughness coefficients resulting from the DPWH, VIMS, and iPhone runs or data. So comparison shows that the proposed iPhone method is comparable with the results of the DPWH and VIMS method, as indicated in the graph, which shows similar trends of highs and lows. Now this is for a target road using the VIMS and the smartphone. And as you can see, you have the comparison between the IRI and also comparable results of iPhone with VIMS with high R values. Now another application in site planning, this is for a sanitary landfill site selection. So these are the steps. So determine first the criteria for sanitary landfill site selection given by RA 9003. You prepare the thematic maps, you conduct spatial analysis, and then last one, you select the suitable areas for SLF. Now the criteria for site selection comes from RA 9003 and it's implementing rules and regulations. The slope, exclude areas with more than 30%. For the built-up areas, must be more than 250 meters away. The potable water sources must be more than 1 kilometer away. NIPAS areas must be more than 250 meters away, and so on and so forth. Okay? We can exclude all those areas. So for example, for slope more than 30%, we exclude built-up areas We buffer it 250 meters away and then exclude. Potable water sources must be more than 1 kilometers away. The water sources exclude. NIPAS areas buffer by 250 meters away and exclude. Lakes and streams buffer by 50 meters, exclude. Flood prone, exclude these areas. Soft sand and highly permeable soils, exclude. Okay, so what is left now is a suitable area for sanitary landfill. Well, of course, you can also consider roads must be accessible from major highways. But if you do that, you also come up with a more refined, suitable area for the sanitary landfill. Now, for land suitability analysis, we have here an example for Taguig City. So you identify the suitable areas for development, and the objective is to determine the spatial distribution and extent of suitable areas based on the following criteria or conditions. A, priority areas shall not be within flooded areas. B, not within areas prone to liquefaction. And C, not within areas prone to earthquake-induced landslide. So basically, we have three hazards here: flood, liquefaction, and earthquake-induced landslide. So we collect data, flood susceptibility data, liquefaction susceptibility data, and landslide susceptibility data, as shown here on your right. So we can assign the weights so that we can take into consideration the different levels of impacts of the hazards. So for example, here we have assigned a weight of 40% for flooding susceptibility, and the rest 30% for liquefaction and landslide susceptibility. And also, we set up a scoring system for the different suitability levels, such as 1 for highly suitable, 2 for suitable requiring minor mitigation, 3 for suitable requiring moderate mitigation, and 100 for not suitable areas. And then we set the scores, and we use the weighted sum overlay tool in GIS, in ArcGIS. So this is simply overlaying the several layers or raster layers together by multiplying each by their given weights and summing them together. So as you can see here, you can set the weights. For flood, it's 0.4, liquefaction 0.3, landslide 0.3. Then click OK, and it will give you your land suitability map. So based on the resulting land suitability map, you can formulate the spatial development strategy. So your land suitability map can also be used to identify suitable buildable areas such as settlements, ecozones. Okay, so I hope that you have learned something from this short introduction of GIS and its relation to planning, especially the various applications of GIS to urban planning. Now, should you have any questions, please do not hesitate to contact me through email. Thank you for watching.